Hi everyone. So we we dealt with Newton's first and second laws in class last Wednesday, and that's like the first third to half of the chapter. Um, I'm gonna dive into the rest of it today in a few videos here. Um, Now, just to remember, the first law was the law of inertia. Inertia means that when an object is in motion, it tends to stay in that motion. If there's no unbalanced force acting on it, it will continue going in a straight line at that velocity indefinitely. The second law kind of adds to that and says if you apply a force to that body, that body will experience an acceleration proportional to its mass. So the mass is a measurement of the inertia. The bigger the mass for the same force, the smaller the acceleration is going to be. Right? And we know that from experience. So the units of force, I'm pretty sure you know this, but just to be clear, force is mass times acceleration. So if we work out the units here in SI units of mass are kilograms, units of acceleration are meters per second squared. So we have kilograms, meters per second squared, and this is defined as a Newton. So that is the base SI unit of force. In terms of what would we say weight, Newton is about the weight of an apple, about a quarter of a pound, just to give you, a sense of that. Okay, so let's dive into section 5.3, combining forces. Okay, there's a couple of things we want to do before we introduce Newton's third law. And one of those is understanding how to combine forces. So forces are vectors. So when you add forces, you need to use vector addition. So use vector addition when adding forces. Okay. If more than one force acts on a body, the acceleration that it experiences is as if there was just one force acting on it. That's the resultant, or the summation of all those forces acting on it. So that force we call F, and that can be called a couple of things. Here we're going to call it F net. Sometimes, I'll put this here in case you see it, where R means resultant. Okay, so summing the forces to one force that is the sum of all those forces. You can see it written a couple different ways. So that F net is just the sum of all the forces that are acting on that body. So a vector addition of F1 plus force 2 plus force 3, yada yada, as far as it goes. So the generalized second law, or the real second law, because before we weren't worrying about what was happening in different directions, but if we take the whole thing in all three dimensions, we have sum of the forces, the net force vector acting on a body is equal to the mass times the acceleration vector. Sorry, there shouldn't be a summation here. It's either F net or sum of the forces, because those are the same thing. Sum of the forces and F net equals mass times the acceleration vector. All right, so since this is a vector, since force is a vector, in 2D, this is two equations, right? You can break that vector into two equations, one in each direction. In 3D, you have three equations, one in each direction. Okay, so you can break some of the forces into these three things. Some of the forces in the X, some of the forces in the Y, and some of the forces in the Z. All right. All right, so let's see how to apply this. We're going to use a hockey puck. Hockey puck acceleration problem. So we have a puck with a mass equal to 0.30 kilograms. It slides on horizontal frictionless ice. All right, so what we're told is there are two forces acting on it. The magnitude of F1 is 5 newtons. The magnitude of F2 is 8 newtons. You are to find the magnitude and direction of the acceleration. All right, so let me show you what they're giving us. This is a 2D problem. Okay, so we have F2 comes up like this. And we have an F1 that goes down like this. So this angle is 60 degrees for F2. This angle for F1 is 20 degrees. This is our X, this is our Y. Okay, so we have the directions and we have the magnitudes of the forces. So let's remember now, the net force is the mass times the acceleration in vector form. So our procedure here is to, what we have to do is find the net force vector. To find the net force vector, you have to break each individual force vector into its x and y components, add those x and y components, and then that will give you the net force vector. So procedure, find the resultant or net force. And that's going to be the sum of the two forces acting on the body. Okay. Then the acceleration is just 1 over m times the resultant force. Okay, so how are we going to find that resultant force? So to find, and this is our standard procedure for a problem like this, you're going to first break each force acting on the body into x and y components. Now, if it was three-dimensional, it would be x, y, and z components. Same procedure. Then you're going to add the x components and add the y components. And if it was 3D, you'd be adding the z components also. And then you find the magnitude and direction of F R. And then once you have that, you can go back up and find the acceleration. That part's easy. Okay, so start with step 1. We're going to start with F1. Let's get our coordinate system back up here. We got an x and y axis. This is our plus x going out this way, our plus y going out this way. We said that our F1 was acting below the x-axis, like that. This was F1. So just some dotted lines to guide the eye. We have an x component to here, and we have a y component here. So this is F1 in the x direction, this is F1 in the y direction. Okay, now we've just gone back to vectors and finding components of vectors. So the component of force 1 in the x direction is F1. Oh, and this angle right here from our problem setup is 20 degrees. Okay, so it's F1 cosine of 20. And that gives us 4.7 newtons. The y component is just the sine of 20, which gives a negative 1.71 newtons. All right, same thing for F2. Let's draw that out. F2, get our coordinate system. Okay, F2 was in the first quadrant here. Oops. Start at the origin and go up to those at 60 degrees, so something like that. It was 60 degrees. If we do our dot to guide the eye to the components. Reminder, this is our x direction, this is our y direction. Get rid of that string vector. So we've got here F2 in the y direction. And here we have F2 in the x direction. So we're going to do the same thing we did for the for force 1. We're going to find the components. So F2 in the x direction is the magnitude of the entire force times the cosine of 60, which gives us 8 cosine 60, or 4. In the y direction, same thing, it's only sine. 8 sine 60 gives 6.93. Okay, so we've broken both of the forces acting on the body into components. So the resultant force is the sum of each of those components. So first, we're going to do the I components. So in the I direction, I just put the unit vector in front just to remember, so to help me remember which ones to use. So F1 in the x direction plus F2 in the x direction plus the j unit vector times the component from force 1 in the y direction plus the component from force 2 in the y direction. And then I've got all those numbers, so I just fill them in. 4.7 plus 4 and negative 1.71 plus 6.93. So F, when we add that up, is 8.7 I plus 5.22 J. Okay, that's the vector form of our resultant force. Now to go back to acceleration, it's going to be 1 over m times the force. So that's 1 over 0.30 times the resultant force, 8.7 I plus 5.22 J. So our acceleration ends up being in vector form, 29I plus 17.4 J. The magnitude of that, square root of the squares, 29 squared plus 17.4 squared is 33.8 meters per second squared. And if we're asked to find the direction also. So making our coordinate system here, we had x and a y. We have an acceleration vector that we know is in the first quadrant because both are positive. So something like that. It's going to have an x component that looks like this. It's going to have a y component that looks like this. So this is the angle we're looking for. And so AX is 29 from up here. AY 17.4. So tangent of the angle is 17.4 over 29. So our angle is 30.9. So in terms of magnitude and direction, the acceleration is 33.8 meters per second squared at an angle of 30.9 degrees relative to the positive x-axis. All right, folks, that's it for now. I'll be back with section 5.4. See you later.